This week we are going to focus on Chapter 15, which is about doing hypothesis tests on parts of models. Remember last week we did tests on whole models. This time we're going to be looking at just individual explanatory variables or covariates that we're putting into the model. So why would we choose to do tests on part of a model instead of on the whole model? There are a couple of reasons. One of them is that the research question might focus on the relationship between one explanatory variable of interest and the response variable, but there are other possible confounding variables that we need to control for, be our covariates. And so we might really be interested in the test only related to the coefficient for the explanatory variable of interest to us. The other reason we might do tests on parts of models are to try to decide which explanatory variables are relevant in a model and which ones might be able to be eliminated to make the model more simple without diminishing its predictive abilities. So the first section in the textbook talks about the term-by-term ANOVA table, and we actually did see these last week. If you remember, when I was modeling the variable a, which is our response variable, as a linear function of b plus c, those were my explanatory variables, we saw that we could use the ANOVA function on that linear model, and it would give us this table that gave us sums of squares and degrees of freedom for each of the individual terms in the model. And what we did with them is we saw how that we could consolidate the rows for the different terms, B and C, and make a whole model ANOVA table that we could then use to calculate this F statistic for our test. This time we're going to be looking at the term-by-term ANOVA table on its own. Now the whole model ANOVA table allowed us to do whole model tests. The term-by-term ANOVA table is going to allow us to do tests on individual terms that we've included in the model. In the term-by-term ANOVA table, there's a sum of squares and mean squares that are calculated for each term in the model. The mean squares is just the sum of squares divided by the degrees of freedom associated with that term. The F statistic for each term is calculated by taking the mean squares for that term and dividing it by the mean squares for the residuals. And then the degrees of freedom used to find p-values from the F distribution are, remember we need numerator and denominator degrees of freedom. The numerator degrees of freedom are the degrees of freedom that are associated with that term in the model. And the denominator degrees of freedom are the residual degrees of freedom. Our textbook separates the model terms into two different types, explanatory variables and covariates. As defined by our textbook, explanatory variables are variables that are specifically of interest to us in answering a research question, whereas covariates are variables that are not specifically of interest to us, but might either enhance, mask, or reverse the role of the explanatory variables. So these are the things that are potentially confounding or effect modifying variables. The textbook talks about the idea that covariates added to the model soak up variance. And essentially what that means is that when you're adding important covariates to the model, they can reduce the amount of randomness that is left over and attributed to the residuals, which will make it easier to see patterns in the data. And also, since our F statistics are always using the variance in the residuals as the denominator, it will also make it easier to find statistically significant relationships between the terms in your model and the response variable. Let's look back at an example from earlier in the semester. Remember, we were looking at how per pupil spending in a state is related to the average SAT score in that state. So our response variable was the average SAT score for each state. The explanatory variable was expend, which was the average per pupil spending in the state. And what we saw was when we fit our linear model, the coefficient for expenditure was negative, which would indicate that spending more on per pupil on schools was associated with lower academic achievement as measured by the SAT score. Now, when we controlled for the covariate frac, which was the fraction of students taking the SAT in each state, then we saw that the coefficient for expenditure changed sign, that once we've controlled for the fraction of students who are taking the SAT in each state, increased student spending is associated with higher SAT scores. And what we can see here is, if we look at our ANOVA table, which we hadn't done previously, is that the sum of squares for expenditure in both of these models is the same. Right? The sum of squares and the mean squares are both the same in both models. What's happened, though, is we can see the F statistic is different in these two models, which means that our p-value is also different. And the reason that they are different is because the residual variance, right, is different. The sum of squares that are attributed to the residuals is much smaller because the fraction of students taking the exam is soaking up a lot of the sums of squares. So a lot of the variation that was originally left unexplained by the model is now being explained by the fraction of students taking the SAT. And so now when I take my mean squares for expenditure and divide it by the mean square of residuals, instead of dividing by 4,887, I'm dividing that same mean square by 1,054, and it's giving me a much larger F statistic value and a much smaller p-value. And in addition, it's also showing me a relationship in the opposite direction. And so it's an example of the covariate frac here soaking up variance and giving us a clearer picture about what the association is between expenditure and SAT scores. Another example that is shown in the book looks at the question, in heterosexual couples, does the age at which a person marries differ between brides and grooms? So in this situation, we're using a data set called the marriage.csv data set. And you can see there are, the age is here. And the variable person here is indicating whether the person is the bride or the groom in the couple. And then we've got the book page ID. Actually, if you look at these, you can see there are 2 observations for each of them. So these are the groom and the bride from the same couple. So our response variable in this case, we're trying to see whether the person is the bride or the groom, explain some of the variation in age. So our response variable is age, and the explanatory variable is person. Now, if we go ahead and fit a linear model with age as the response variable and person as the explanatory variable in this marriage data set, we can see we've got a coefficient on groom of 2.545. So what this is indicating it to us, keep in mind this is a group-wise model because we've got a categorical variable here. So remember, the intercept here would be the average age of the women in the sample when they got married. And here's the average age, the difference in the average age between the grooms and the brides. So the average groom was 2.54 years older than the average bride. So again, from the coefficient, you can see that among people in the sample, the average age among grooms was 2.54 years older than the average among wives. However, we can also look at our analysis of variance table. And we can see that the person variable, when we do a hypothesis test to see if this is a statistically significant difference, if this is contributing in a significant way to the model, we have a p-value of 0.384. So that is a very large p-value, indicating weak evidence that there's a difference in the mean age between brides and grooms. So the p-value for our F-test tells us there is not statistically significant evidence that in the population from which this data were collected from, the age at which a person marries differs between brides and grooms. And this type of F-test is equivalent to a t-test comparing means from two samples. So if you've taken another statistics course where you did a two-sample t-test, this is an equivalent test. It would give you exactly the same p-value as a two-sample t-test, assuming that the variance is equal in the two groups. So in this example, if we add a covariate, the book page ID. Now, if you remember what this did, this was a variable that took on a different value for each couple. So what we're doing now by doing this is we're controlling for couples. So we'd be thinking like, okay, among individual couples, is there a difference in age between brides and grooms, the person and the couple? Now what you can see this did, as I'm looking at my analysis of variance report, the degrees of freedom, the sum of squares, and the mean squared are the same for person as they were before. The variance that was left over in the residuals, you can see the sum of squares and the mean squared are much smaller than they were before. And the variable that is identifying which couple the data came from is soaking up a lot of the variability because couples tend to be close in age to each other, right? An older person will tend to marry someone who is also older. A younger person will tend to marry a person who is similar in age. So when we look at it this way, by soaking up the excessive variability that comes between couples in this book page ID, what it's doing is it's making so that when I'm calculating my F statistic, I'm taking the mean square for person and dividing it by a much smaller value for the mean square of the residuals than I had before when I wasn't controlling for book page ID. This gives me a larger value for my F statistic and a much smaller p-value. And so by accounting for the variability between couples, there's a statistically significant result. So we can say that there's statistically significant evidence that among people in the same couple, because we're controlling for which couple they're in, grooms tend to be older than brides. Now there's one funny thing that you should know about term-by-term ANOVA tables, and that is that the order that you enter the terms in the model is going to impact the sum of squares, mean squares, and F statistic for each term. So not only which variables are in the model together, but the order in which you type them into R is going to make a difference. I'll show you what I mean. Here, I'm looking at my response variable SAT as a function of expenditure plus frac. here in my alternative, I've got the same two explanatory variables, but I have changed the order. So instead of expend plus frac, I have frac plus expend. If you look at it, what you'll see is that this didn't change the intercept. It didn't change the coefficient for the fraction of students taking the SAT, and it didn't change the coefficient for expenditure. But what it did do is it changed the sums of squares and the mean squares and the F value and the P value. So for instance, if I look at expend in this model, the sum of squares is 39,722. In this model, it's much smaller, 8,913. My F statistic, which is my mean square divided by my mean square for the residuals, which notice the residuals are the same in either case. But my F statistic is much larger and my p-value is much smaller when I put expenditure into the model first compared to when I put it in second. On the other hand, the sums of squares for frac are much smaller here in the model where it was entered second than they were in the model where they were entered first. And similarly, the F statistic is smaller in that situation as well. So this is one of the strange things about term by term ANOVA tables, is that although it's not going to change how your model is fitting, what the fitted values are or what the residuals are, it is going to change the term by term ANOVA table that you get, depending on whether I enter frac plus expend or expend plus frac. Okay, so why does this happen? Why do we get different sums of squares for the different terms depending on what order we put them into the model? So the reason that this happens is because when we're doing the term by term ANOVA table, the calculation of the sums of squares are done by treating the models as nested in the order that the terms are added to the model. So for example, if I'm looking at my model, I start off and say, okay, well, let's fit a model with just an intercept. Remember when we have a tilde1, that's an intercept only model. And so over here I can see that when I do my analysis of variance for that, I find that the only term is the residuals. And so the sum of squares for the residuals is 274,308. So next thing it does, it says, okay, if I have my final model here is going to be that SAT scores are going to be a linear function of expenditure plus the fraction taking the SAT. So I've already done it with neither of these terms in the model. Now I'm going to look at what the model would look like with adding just expenditure. So when I do that here, I've got the linear model SAT as a function of expenditure. Now the way that it's going to calculate the sum of squares for expenditure is by taking the sums of squares that were in the residuals from the previous model, subtracting off the sum of squares for the residuals in the new model, and then the difference is the sum of squares that are attributed to expenditure. Right, so we have 274,308 minus the sum of squares in the residuals once we put expenditure in the model, and this becomes the sum of squares that are associated with expenditure. Then we say, okay, so now let's see how much the sums of squares of the residuals are further reduced by adding frac to the model. Those are the sums of squares that are going to be attributed to frac. So to do that, we take the sum of squares in the residuals here, and we see how much it's reduced by adding frac to the model. So the sums of squares for frac in this model, we're taking the sums of squares for the model with expenditure but without frac, subtracting off the sum of squares for the residuals with expenditure and frac in the model. And that difference that we get is the sums of squares that are attributed to the fraction taking the SAT. And so essentially we're saying, okay, how much further are the sums of squares reduced by adding frac to the model when expenditure is already in it? Now, if we do them in the opposite order, so now when I switch and I say, okay, now I want to have SAT as a function of the same variables, but in the opposite order. So frac plus expend. Now what it's doing is when it's finding the sums of squares that it's associating with frac, it's saying, okay, compared to the model that didn't have any explanatory variables in it, this one here, how much was the sum of squares and the residuals reduced? So I take the sum of the squares residual for the model with no covariates. I subtract off the sum of the squares of the residuals for the model that has frac in it, and that difference gives me the sum of the squares that are associated with frac. So this is different because remember before it was saying, okay, how much further were the residuals being reduced by adding frac to a model that already had expenditure in it. But now I'm adding frac to a model that has no explanatory variables in it. And so the sums of squares that are attributed to it are different. And the same will be true here. As I put in expenditure, the sums of squares that are going to be attributed to expenditure are going to be, okay, how much smaller are the residual sums of squares compared to the model that included frac? So we take the sum of squares for the model that had frac in it, and we subtract off the sum of squares residuals here for the model that had both frac and expenditure in it. And it gives us a change between these two models in the residual sums of squares of 8,913, and that is what's attributed to expenditure. Right? So because of this thinking about sort of how much does the next term improve the model, how much more of the variation is being soaked up by this model now that I've added this next covariate, that's why the order that we do this matters in terms of what happens with our ANOVA table. And so, this is a little bit disconcerting, and it makes it a little bit hard to interpret tests that are done based on these type term-by-term ANOVA models, because the p-value and the conclusions that we draw from the tests are going to be dependent on the order that we put the terms in. So again, we've seen how this happens, why it happens in terms of the way that R does its calculations. But, in the bigger sense, why does this happen? Well, it happens because there is some collinearity between the variables that we put in this model. And what that means is it means that it's not really clear to which of the related variables we should give the credit for reducing variability in the residuals. And so that's what happens. So if we didn't have any collinearity between the variables and they were completely orthogonal to each other, then we wouldn't have this issue. But unless we can work in a situation where we have a lot of control over the different terms in the model, for instance, in a really well-designed experiment, maybe you could eliminate some of this collinearity, but otherwise it's going to happen most of the time that you have at least some collinearity between the variables in the model. And so the order in which you include the terms is going to impact the term-by-term ANOVA table. Sometimes the fact that the sum of squares depends on the order that the terms are put into the model can actually impact whether the test for an individual term is statistically significant or not. So I'm going to use an example that they had in the textbook. Is a person's height related to the number of children in their family? And they lay out in the textbook some reasons why they might be. There might be more competition for food, say, in a family that has more children. So maybe each child gets more to eat if the children are sort of in equally well-off families. Or it could be the other way. Maybe families with more children tend to be families that are more well-off, and so maybe there's more food available. I guess they kind of had hypotheses that could explain a difference in either direction. So important to do a two-tailed test so we could pick up a difference in either direction. Now, if we are thinking about height, we know that height is also related to a person's sex, their father's height, and their mother's height. We have all of those in the data set. So even though we're primarily interested in the number of children as our explanatory variable, we are also going to be interested in sex, father's height, and mother's height as covariates. So if we fit a model that models height as our response variable, and then puts in the explanatory variable for the number of kids, and then the covariates after that in R, we see that if we look at the F-test statistic and p-value for this individual term, number of kids, we have a very small p-value, which would give us a statistically significant result. So let's think for a minute about how the sum of squares was calculated and what hypothesis that's really testing. So the null hypothesis for this test, since this sum of squares is calculated by saying, okay, what would be the sum of squares for the residuals in a model that had no terms in it, and how much was it reduced by adding a term for the number of kids in the model, and only number of kids. Right, so what this is really testing is it's testing to see how strong the evidence is that against this null hypothesis that a model with the number of kids in it is no better than a model without any terms. And we can reject that null hypothesis, which is telling us that putting the number of kids into this model was an improvement over not having any variables in the model. Now, on the other hand, when we, instead of putting the number of kids as the first term in our model, move it to the last term, adding the covariates first, we can see that the number of kids has a much smaller sum of squares associated with it, a smaller F statistic, and because of that, a larger p-value. And this happened, remember, because now instead of saying, okay, how much was the sum of squares reduced from a model that has no terms in it to a model that has the number of kids in it, now it's saying, okay, how much was the sum of squares and the residuals reduced by taking a model with sex, father, and mother's height in it, and then adding the number of kids to that model. Right? So here we can think of the null hypothesis that we're testing is that a model with the number of kids, sex, father, and mother is no better than a model that has all of those other covariates, but not number of kids, so sex, father, and mother. And in this case, our p-value is too large, so we can't reject the null hypothesis. So we would say that there's not evidence that a model with a number of kids included is an improvement over the model that included sex, father, and mother, but did not include the number of kids. Right? So we have this sort of weird, ambiguous result, and depending on which order we put the terms in, number of kids could go from being a statistically significant contributor to the model to one that's not statistically significant. So we've seen that this changing sums of squares depending on the order of the terms being put into the model creates ambiguity. What are some ways that we could use to try to reconcile this ambiguity? One of the methods suggested by the textbook is to treat ANOVA with this term-by-term method as a screening test to give us a way to try to probe what variables might be useful to include in a model, and also what covariates might be useful to include in a model. So that's one idea. Another one is to try to eliminate the ambiguity altogether by using an experimental design that will eliminate collinearity between variables. Another suggestion is to adopt a skeptical attitude, that is to pick the ANOVA table that makes your explanatory variables have the smallest sum of squares. That would generally be by putting it into the model last. And then see if you still have a statistically significant result. Another thing that was mentioned was adopting what they called an enthusiastic attitude toward hypothesis formulation. Essentially, using this and saying, hey, I see a statistically significant result in this particular version of the term-by-term analysis of variance table. Maybe there's a reason for that. Think about, sort of what you know about the system and what might support that theory, and then collect some more data to test it in a more rigorous way. Another thing is to remember that knowledge of how the system works and how the variables should be related to each other is helpful. And so instead of thinking about trying to just blindly model relationships in the data, use knowledge about how the system works that you might already have to model the system using the data, then rather than trying to just fit the data. And then the last suggestion is just to remember that this is just one ambiguity when we're dealing with models. In reality, there are many other ambiguities as well. For instance, how did we decide to measure a particular variable? Which variables did we decide to include as covariates? Did we include an interaction term? Did we include a transformation term that might capture nonlinearity? All of these choices will affect the sums of squares for the other variables in the model. And so, it's not only the choice of the order and this ambiguity that comes up in the ANOVA table, but remember that we always have to realize that there's uncertainty about whether our model is the right model or the best model that we could be using to describe this system. And so those ambiguities are also important and shouldn't be forgotten. T-tests done on the coefficients for the model terms give us another option besides those F-tests from the term-by-term ANOVA table for testing just part of a model. Whenever we do a coefficient t-test, the null hypothesis is that in the population, the coefficient for the model term is equal to 0, but all of the other coefficients are exactly as given by the model fit. So, kind of thinking about that, it means that given that the rest of the model is correctly specified, then there's no linear association between the term that we're doing the test on and the response variable. So we saw that with the F-test from that term-by-term ANOVA table that the p-values depended on the order in which we put the terms into the model. You might be wondering if that is true in this situation also, and the answer is no. The p-values will be exactly the same for these coefficient t-tests, no matter what order we enter the terms in our model. And we can see that here. As we look at our model, here's looking at height with a number of kids, sex, father plus mother. Here we've got the same model with number of kids entered last. And if we just look at the coefficients, the standard errors, the t-test statistics and the p-values, they are exactly the same when we entered it first or we entered it last. So is a person's height related to the number of children in their family? We have our output. We're interested in the number of kids as our explanatory variable. We've included these covariates in the model to control for them. You can see the p-value testing to see if the coefficient for the number of kids differs significantly from 0 is 0.107. So this is a large p-value, which gives us weak evidence. If we were testing at a 5% level of significance, we would not reject the null hypothesis. So we'd say that there is not strong evidence that the number of children in the family is related to height, assuming that the model correctly reflects the relationship between a person's height and their sex, mother's height, and father's height. So we can see that, not having the p-values depend on the order in which we enter things into the model would be an advantage of these tests. And another advantage is I can put a whole bunch of different explanatory variables and covariates into a model. For instance, here I'm using the CPS data that we've been using throughout the semester, and I'm modeling wage as a function of sex, education level, race, whether the person's Hispanic or not, whether they live in the South or not, whether they're married or not, and their experience level. And I've got p-values for t-tests on each of those individual terms, right? So it allows us to conduct tests on each of the coefficients all at the same time. This can be really helpful for screening purposes to look through and say, okay, which of these variables look like they're really important in describing, explaining variability in wage, and which ones look maybe not so important. A couple of things to remember. Have to be careful about multiple testing. Remember, we talked about the idea that if every test is done at a 5% level of significance, and I do a whole bunch of tests, the chance that I'm making at least one type 1 error increases. So really I should do some sort of adjustment for multiple tests. In this case, I've got 1, 2, 3, 4, 5, 6, 7 variables that I put into the model here. So I could potentially divide this by 7 to do a Bonferroni correction and use that as my significance level for my individual tests. The other thing you need to be aware of is that the coefficients, right, the estimates, we saw that those change depending on what other variables in the model. The standard errors and the p-values are also going to change depending on what other variables are included in the model. So for instance, if I were to take this Hispanic variable out of the model, it may be that this race variable changes in terms of its coefficient and its p-value, and it might show as statistically significant. So, we still are going to have situations where we're assuming that the model is correct otherwise, besides the term that we're doing each individual test on. If we start changing what that model looks like, we're going to end up with a different test. And then the last thing to kind of remember about this is that just because collinearity doesn't make it so that the p-value depends on the order that I put things in, doesn't mean that the problem of collinearity has gone away. One thing that will happen when you've got collinearity is when we include collinear variables in a model, all of the standard errors will be made larger, and as a result, the value of the t-statistic will be smaller because we'll be dividing by a larger standard error, and our p-values will end up bigger, so they will look less statistically significant. So remember, in that last model we were looking at with wage, we saw age and education were both in that model, but experience was not. When we do a model with age, experience, and education, because there's so much collinearity between these three variables, we have much larger standard errors, and we have large p-values, and if I didn't know better, I might look at this and think, well, it looks like none of these variables is a particularly, is there evidence that it's strongly associated with wage, right? And so it can be misleading to focus just on these t-tests. Now, a couple of things you can do to avoid sort of missing these things. One is to actually look at those term-by-term ANOVA tables and see what happens when you change the order of things, right? But the other thing that you can do is you can kind of notice that down here, if I look at my whole model test, I can see I've got a very tiny p-value on the whole model test, even though it appears that none of these explanatory variables are close to achieving statistical significance. That can sometimes be a clue that you've got some collinearity going on and that you should rethink whether you want to include all of these variables in your model. Before Thursday's live meeting, please complete as much of homework 10, which is due Thursday night, as you can, because I will answer questions about it during class time on Thursday. Also, get as much work done on your project as you can. That is due on Friday night, and I am not giving you exercises to start before the live meeting this week so that you have more time to spend working on your project. The Chapter 15 exercises we will begin during the live session on Thursday, and it will be homework to finish them up before the following week. Have a good day.